Ready to become a flight instrument pro.
I think we can definitely get you there.
We're going deep today.
Uh,
Using the FAA Handbook.
a classic.
Yeah, a classic for a reason, though, right? To explore how planes can actually fly,
Absolutely.
even when you can't see a thing.
Yeah.
We're covering it all from the Pitot-Static system to the gyroscope.
Oh yeah, all the big ones.
Have you ever wondered what happens
Hmm.
when that pitot tube gets clogged?
It's not pretty.
It's not good.
Yeah, it's definitely a situation.
It can get very bad.
Yeah, you want to avoid that. Thankfully, the FAA handbook
Oh, yeah.
really breaks it down.
Yeah, it's great.
Not just how they work, but how to spot problems.
Yeah,
Before they become serious.
before they become huge problems. Okay, let's jump into it.
All right.
Let's start with the pressure-driven instruments. You know, the Pitot-Static family.
Okay.
Can you give us a quick rundown of how those work?
Yeah, so imagine you're sticking your hand out the window
Okay.
of a moving car. The faster the car goes, the more the air pushes against your hand, right?
Yeah.
That's basically what the pitot tube is doing. It's this little sensor mounted on the outside of the plane, and it's measuring that air pressure, that force of the air, and that directly translates to how fast the plane is going. That's your airspeed.
That's a really simple way to think about airspeed.
Yeah, it's very intuitive.
What about static pressure? Where does that fit in?
Static pressure is like the baseline. It's that undisturbed air all around the plane.
Okay.
So think of it like putting your hand out the window. When the car is parked,
Got it.
there's still air pressure there.
Right.
And by comparing that ram air from the pitot tube to the static pressure, you can figure out a lot.
Yeah.
So instruments like the airspeed indicator, altimeter, vertical speed indicator, those all rely on that difference.
So it's all about those pressure differences.
That's the key.
Like when our ears pop.
Exactly.
When we change altitude.
Yeah, but much more precise.
Yeah, way more precise. What happens if those pressure readings get messed up? Like a bird builds a nest in the pitot tube, or ice clogs a static port.
That is a good question, and it's not good.
That's a thought that makes me nervous.
Yeah, it's a problem because a blocked pitot tube can really mess with the airspeed indicator.
Yeah.
So it might show an increase in speed when you're actually climbing, even if the speed is constant, or even worse, it could drop to zero even though the plane is still moving through the air.
Oh man, that's terrifying.
Yeah, it's not good.
Especially if the pilot doesn't realize.
Right, and a blocked static port is just as dangerous because it can make the altimeter freeze, so you get a false reading of your altitude. And the vertical speed indicator might flatline even if you're changing altitude.
Oh my God.
It's like driving with a broken speedometer and a faulty GPS.
Yeah.
You have no idea how fast you're going or where you are.
It makes you appreciate those pre-flight checks.
Absolutely.
They're not just a formality. It's about safety.
Yeah, you got to make sure those systems are giving accurate readings.
Absolutely. And it's not just about those tubes. It's also about how these instruments interact.
Yeah, that's a good point.
You know, there was a tragic case.
Right.
Back in 2009, Air France Flight 447
Right.
blocked pitot tubes, played a role in a devastating crash.
Yeah, and it shows how important it is to really understand these systems inside and out.
Sobering reminder
Yeah.
that it's all about safety.
Right, because at the end of the day,
Yeah.
these instruments are there to keep us safe. That's where the alternate static source is so important.
Oh yeah, tell us about that.
So if the main static ports get blocked, the pilot can switch to a backup source, which might not be as accurate as the primary,
Yeah.
but it can still give you readings in a pinch. It's like a spare tire.
Yeah, you hope you never need it, but it's good to have it.
Exactly.
Okay, so pressure is key for understanding airspeed and altitude
Right.
and vertical speed. But pressure doesn't tell us which direction to fly, does it? For that, we need to talk about compasses.
Right.
And not just any compass.
Yeah.
The OG of navigation,
Yeah.
the magnetic compass.
The classic. Still a vital tool even today.
I love it.
Eh.
It might seem simple, but there's a lot more to it than just pointing north.
Oh, there's definitely some nuance to it.
Well, that's why we're here,
Right, exactly.
to uncover the not-so-obvious stuff.
Yeah.
I mean, I know how basic compass works, but how does that translate to flying a plane?
Well, for starters, unlike the compass you might use for hiking, the compass card in an airplane is fixed. It doesn't actually spin. So imagine like a big clock face
Okay,
mounted horizontally in the cockpit.
got it.
The plane and the pilot rotate around the card, and you read the heading by seeing which degree mark lines up with the lubber line,
Yeah.
which is a fixed reference point.
Okay, so it's like the plane is the minute hand on a clock,
Yeah,
and the compass card is the clock face.
exactly.
Got it. Why do we always hear about these compass errors? Doesn't a compass just point north?
I wish it were that simple. Unfortunately, magnetic compasses have a couple quirks that we need to account for: variation and deviation.
Okay, let's break those down one at a time.
All right.
What's variation?
Variation is the difference between true north, that's the geographic North Pole where all the lines of longitude meet,
Yeah.
and magnetic north, which is where your compass needle actually points. Because the Earth's magnetic field isn't perfectly aligned.
Right.
Those 2 points don't line up perfectly, and that difference, we call that variation.
So the compass isn't really pointing in the right direction.
Well, it's pointing towards magnetic north,
Yeah.
which is close to true north,
Okay.
but not exactly the same.
How do pilots deal with that?
They use charts that show lines of equal variation. They're called isogonic lines.
Okay.
It's kind of like a topographic map, but instead of showing elevation, it shows how much your compass will be off,
I see.
depending on your location.
That's clever.
Yeah, it's a way of correcting
Yeah.
for the Earth's magnetic field being a little wonky.
Now what about deviation?
Deviation is all about those little magnetic fields
Okay.
within the aircraft itself.
Right.
All the electrical currents and equipment create their own mini magnetic fields.
Yeah.
And those can mess with the compass, throw it off.
So it's like trying to use a compass next to a giant electromagnet.
Pretty much.
Bound to get confused. How do pilots account for that?
Well, it's all about calibration. They do this thing called swinging the compass, where they basically align the plane with known magnetic headings, and then they fine-tune the compass using these little magnets
Wow.
inside the instrument. So they're basically tweaking it
Okay.
to reduce the interference.
So it's like giving the compass glasses to correct its vision.
Yeah, a good analogy. But even with those corrections, are there other things that can throw a compass off?
I would imagine so.
You're right, there are a few other errors, stemming from the fact that the compass card is actually suspended in fluid,
Okay.
and that can be affected by the plane's movements.
Yeah.
Things like acceleration error, where speeding up or slowing down on an east-west heading
Okay.
can make the compass think you're turning, or northerly turning error, southerly turning error.
Right.
It can get pretty complex.
So reading a compass in a plane is not as simple as it seems.
No, it's not.
You need to know a little bit about physics.
You gotta know your stuff.
But the key is that pilots need to be aware of these issues
For sure.
and understand how to work around them.
Awareness is key.
Okay, so the magnetic compass, while classic,
Right.
it has its limitations.
It does.
What did they come up with to improve on it?
Well, enter the flux gate compass,
All right.
which ditches the magnets entirely and instead uses electricity
Okay.
to sense the Earth's magnetic field,
Okay.
giving a much more stable and accurate reading.
I'm all ears. How does
Oh.
that work? Is there like a magic sensor?
Well, it does have a special sensor. It's called a flux valve,
Okay.
and it's usually mounted way out on a wingtip, far away from all the electrical interference inside the plane.
Right.
And the flux valve uses coils of wire
Mm.
and a core of soft iron to interact with the Earth's magnetic field.
Okay.
And that induces a current
Yeah.
that directly translates to the plane's heading.
So it's like the Earth's magnetic field is whispering the heading
Yeah. It's a good way to think about it.
to the instrument.
Yeah.
That's a lot more sophisticated than just a simple magnet.
It is. And because it's out on the wing, it's not getting messed up by all the electrical stuff
Right.
inside the plane.
That makes sense. So it's less prone to those errors we talked about.
Yeah, much less.
Okay, great. But how does the pilot actually see that heading information?
Good question. That's where instruments like the RMI and the HSI come in, radiomagnetic indicator, and horizontal situation indicator.
Okay.
They take that heading from the fluxgate compass and combine it with other navigation signals, like from VORs and DMEs,
Yeah.
to give a much more complete picture
Okay.
of where the plane is and where it's going.
So it's like a compass and a GPS all in one.
Yeah, kinda.
Pretty cool.
Yeah.
We've covered pressure. We've covered magnets.
Well-
Now it's time to talk about something that's always been a bit mysterious to me. Gyroscopes.
Yes. The wonderful world of gyros.
Yeah.
Get ready for some physics.
I'm excited. Gyroscopes they're the backbone of so many crucial instruments.
Yeah, they really are.
And they might seem like magic, but they're based on some really fascinating physics.
It's true. And they have these 2 key properties.
Okay.
Rigidity and precession.
All right, break it down for us.
Okay.
What is rigidity when it comes to a gyro?
Okay, so imagine you've got a spinning top.
Right.
You try to tilt it over,
Yeah.
but it resists, right?
Yeah, it wants to keep spinning
Exactly.
in the same way.
It wants to stay upright. That's rigidity in action. A gyroscope is basically a spinning wheel mounted in a special frame.
Okay.
And it does the same thing. It wants to keep its orientation, no matter how the plane moves around it.
So even if the plane is pitching and rolling, the gyro inside stays put.
Exactly.
That's crazy.
It is, and that makes it perfect for things like the attitude indicator,
Okay.
which tells the pilot the plane's orientation relative to the horizon.
So it's like an artificial horizon.
Yeah, it's a great way to think about it.
Right there in the cockpit,
Mm,
even when you can't see the real horizon.
right.
Okay, now what about precession? What's that all about?
Precession is where things get interesting. Basically, when you apply a force to a spinning gyro, it doesn't move the way you expect. It moves at a right angle to that force.
Wait, what? So if you push a gyro to the left, it moves up or down?
Yeah, you got it.
That seems counterintuitive.
It does, but that's how it works. Picture a spinning bicycle wheel. If you try to tilt the wheel to one side, it actually turns in a different direction.
Wow.
Yeah, it's kind of a mind bend. And it's that quirk
Okay.
that makes gyros so valuable for instruments like the turn coordinator,
Got it.
which tells you how fast the plane's turning.
Okay, I see why they call them gyroscopic instruments.
Ah,
It's not just the spinning, it's those unique ways they behave.
exactly. It's all about the physics.
So if these spinning gyros are telling us the plane's orientation and turning rate,
Mm-hmm.
how does the pilot actually see that?
Well, let's start with the attitude indicator, also called the artificial horizon.
Okay.
At its core is a gyro,
Huh.
spinning on a vertical axis. And it's mounted in these things called gimbals,
Okay.
which allow it to stay upright,
Yeah.
even as the plane moves around it.
Okay.
Attached to that gyro is a horizon bar, which moves with the gyro.
Okay.
So as the plane pitches up or down, that horizon bar on the instrument moves up or down, giving you a visual of where the real horizon is, even if you can't see it.
So it's like a little window
Yeah.
into the plane's orientation,
Yeah, a good way to think about it.
even when you're flying in the clouds.
Yeah, especially when you can't see outside. It's vital
Yeah, absolutely.
for maintaining control in instrument conditions.
Okay, so the attitude indicator gives us orientation. What about knowing our heading when we're relying on these gyros?
Well, for that, we have the heading indicator.
Okay.
It uses a gyro that spins on a horizontal axis. And thanks to rigidity, this gyro wants to stay fixed
Yeah.
in its orientation. But unlike the magnetic compass, it's not affected by the Earth's magnetic field.
So it doesn't have those variations.
Exactly. No variation, no deviation.
That sounds perfect.
Well, almost. The catch is that the heading indicator has to be set manually.
Okay.
You have to use the magnetic compass as a reference.
Right?
Think of it like setting your watch.
Yeah.
You have to check it against a reliable source
Okay.
because the heading indicator can drift
Yeah.
over time. So pilots need to reset it to the magnetic compass every 15 minutes or so.
So it's a team effort.
Yeah, they work together.
The heading indicator gives a stable reading, but needs that reality check
Yeah. Got to make sure it's still accurate.
from the magnetic compass. Makes sense. But what about turning? Is there a gyro for that?
There is. And this is where precession comes into play.
I was wondering when we were going to get back to that.
It's pretty cool. The turn indicator uses a gyro mounted, so its axis
Okay.
is parallel to the plane's lateral axis, that imaginary line running wingtip to wingtip.
So we've got this gyro lined up with the wings. What happens next?
Imagine the plane starts to turn. That turning force is applied to the gyro.
Okay.
But thanks to precession, the gyro doesn't actually tilt in the direction of the turn. It tilts forward or backward,
Wow.
depending on which way you're turning.
That's amazing.
And the amount it tilts is proportional to the rate of turn. So the faster you turn, the more the gyro tilts.
So the gyro is doing a little dance
Yeah, you can think of it that way.
to show how fast the plane is turning.
Right.
And that's what moves the needle
Got it.
on the instrument.
What about that little inclinometer ball?
Ah, yes, the inclinometer.
Yeah.
Something's called the coordination ball.
Right.
It's basically a little spirit level
Right.
inside the turn indicator.
And it tells you the relationship between the bank angle and the rate of yaw.
Okay.
So it shows you if you're turning smoothly or if you're kind of slipping and sliding through the air.
So keeping that ball centered is all about having a nice smooth turn.
Yeah, it's about coordination,
Right.
making sure everything is balanced. And it's key for a comfortable and efficient flight.
Got it. All this talk about spinning gyros, I have to ask, how are they powered?
Good question. They got to spin pretty fast to do their thing. And there are two ways to power them: pneumatically, using air, or electrically,
Okay.
using a motor.
All right, so let's start with pneumatic. How do you power a gyro with air?
Some planes use a vacuum system.
Yeah.
where an engine-driven pump sucks air through the instruments.
Okay.
The airflow goes through these little nozzles, creating a mini turbine effect
Okay.
that spins the gyro.
So it's like blowing on a pinwheel, but instead of a pinwheel, it's a high-precision gyro.
Exactly.
That's so cool.
Mhm.
What about electrical power? Is that more modern?
It is. Electrically powered gyros have little motors built right in.
Okay.
No need for air, just electricity
Yeah.
from the plane's electrical system. And they have some advantages. They tend to be more reliable because they have fewer moving parts.
Right.
And they're not as affected by things like moisture or leaks.
So it's like the difference between a wind-up clock and a battery-powered watch.
Yeah.
Do most modern aircraft use pneumatic or electric?
It depends on the plane.
Okay.
Some use one or the other, and some use a mix of both for redundancy.
Redundancy is so important when it comes to flight instruments.
Oh, absolutely. Pilots need to be able to rely on these instruments even if one system fails.
Okay, we've covered a lot with these basic flight instruments. We've seen how pressure differences tell us about speed and altitude, how magnetic fields and sensors help us stay on course,
Yep.
and how these amazing gyroscopes can mimic the horizon
Mm-hmm.
and tell us how we're turning.
It's pretty amazing technology when you think about it.
But we've really only scratched the surface, haven't we?
We've laid the groundwork. But there's a whole world of advanced systems out there, things that take these basic principles
Right.
and supercharge them with digital text satellite navigation and even artificial intelligence.
And that's where we're headed next. From FMS to TOS, we're going to explore how technology is making flying safer, more efficient, and even more automated than ever before.
Yeah.
We've explored the foundations, those slight instruments that have been guiding pilots for so long.
Mm-hmm.
But aviation never stands still, right? It's all about pushing boundaries.
It's a spirit.
So what's next for these systems? What's on the horizon?
Well, it's incredible how technology keeps evolving, Those traditional instruments we talked about, they're still vital, but they're often working alongside these advanced systems now, bringing a whole new level of capability and safety to flying.
So let's talk about some of these game changers.
Okay.
You mentioned flight management systems, FMS.
Right?
What are those all about?
So imagine like a super-powered GPS, but designed for aviation. That's the essence of an FMS. It takes all that navigational data from GPS, VOR, DME, all of it, and combines it to create a really detailed flight plan.
It's just like a personal air traffic controller right there on board.
Pretty much. But it does way more than just show you where you are and where you're going. It factors in wind conditions, calculates the most fuel-efficient route, predicts arrival times really accurately, and even talks to the autopilot to fly the plane along that path.
So it's not just about navigation, it's about optimizing the entire flight.
Exactly, making it as smooth and efficient as possible.
I can see why those are so important, especially for long flights.
Oh yeah, they're crucial for long haul.
But what about safety? Are there systems that can help prevent those really bad scenarios?
Absolutely. Safety is paramount in aviation, and that's where systems like TOBUs come in. Terrain awareness and warning system.
Okay.
It's like a virtual guardian angel looking out for the plane, making sure you don't run into the ground.
You had me at Guardian Angel.
That's a good one, right? So TALOS uses GPS data and this incredibly detailed database of terrain and obstacles.
Wow.
And it's constantly building a 3D map of the world around the plane and comparing the plane's position and trajectory to that map.
Okay.
If it senses a potential conflict, it issues these warnings, giving the pilot time to adjust course or altitude.
That's huge. It's so much better than those old ground proximity warning systems.
Right.
The ones that just yelled, "Full UP."
Right. TALA is much more proactive.
Yeah.
It anticipates problems before they even happen. And that's a game changer when it comes to safety, especially in mountains or low visibility.
All right, so we've got systems to help us avoid mountains.
Right.
What about avoiding other airplanes?
Another great question. That's where TCS comes in, Traffic Alert and Collision Avoidance System.
TTS, okay.
It's all about preventing those near misses in the air. It's like air traffic control radar, but right there in the cockpit.
That's amazing. How does that work? Does it actually talk to other planes?
It does. It uses transponders, which are like little radio beacons that transmit the plane's ID, altitude, position. And the TCS system is listening for those signals from other aircraft, and it displays them on a screen.
So it's like having a little radar screen showing you all the planes around you.
Exactly. Gives you that extra awareness, especially in busy airspace.
Yeah, I bet that's reassuring.
It is, but it gets even better.
Okay.
If it detects a potential conflict, it warns the pilots. And it can even suggest maneuvers.
Really?
Like climb, descend, turn, things to avoid a collision.
It tells you what to do.
It does. And the really cool part is that TCS systems on different planes can actually talk to each other to coordinate those recommendations. So you don't have both planes trying to do the same thing and ending up colliding anyway.
Wow. So they work together to make sure everyone stays safe?
Exactly. Team effort up there. It's no wonder it's been so effective.
Yeah, that's incredible. What about situations where visibility is super low, like flying through thick clouds or fog? How can pilots see in those conditions?
Well, that's where we get into the really futuristic stuff like synthetic vision systems.
Yeah, I've heard about those. Do they actually give you X-ray vision?
Not quite X-ray vision, but it's getting close. So synthetic vision takes GPS data, terrain databases, and some very impressive computer graphics and combines them to create this real-time 3D view of the world outside.
So even when you can't see anything?
Even then,
Wow.
it can show runways, taxiways, mountains, obstacles, the whole picture. And that virtual view is displayed right on the primary flight display.
So it's like a video game, but in real life.
Yeah.
Showing you the terrain, even if you can't see it out the window.
Yeah.
That has to make landing a lot easier.
Oh, it does. It makes those approaches much safer.
Yeah.
And less stressful for pilots. And it's not just for bad weather, it's also useful at night or in unfamiliar terrain.
Okay, so it's like having this extra set of eyes that can see through clouds and darkness. That's pretty remarkable. We've been talking a lot about what's happening outside the plane. But what about communication? How do pilots stay in touch, especially in remote areas with limited radio coverage?
That's a great point. And it brings us to ADS-B, Automatic Dependent Surveillance Broadcast.
ADS-B. I've heard that term.
It's a newer technology, but it's changing things rapidly. Think of it as a sophisticated GPS tracker. But for airplanes, with ADS-B, planes are continuously broadcasting their position, altitude, speed, all of that data to ground stations and to other aircraft equipped with ADS-B.
So everyone knows where everyone else is all the time. That seems like it would be huge for air traffic control.
You're exactly right. It gives controllers a way more accurate and detailed picture of what's happening.
Yeah.
And because it doesn't rely on radar, it works even in those remote areas or over the oceans.
Wow. So no need for line of sight?
Nope. Just constant communication.
What are some of the benefits of that?
Well, for one, it makes flying safer. Pilots have a much better sense of where other planes are, which helps prevent those near misses. And it can also make flying more efficient.
Okay, how so?
With that precise tracking, you can have more efficient routing and spacing of aircraft, which can reduce delays and save fuel.
That's pretty impressive.
It's a win-win.
Yeah. So ADS-B really seems like it's the future of air traffic management.
It's becoming the standard. And as more aircraft get equipped with it, it's only going to get better.
It's incredible how these new technologies are changing the cockpit. With all these systems working together, it's almost like having a whole team of co-pilots up there.
It's pretty remarkable. We've come a long way from those basic instruments.
Absolutely. And the pace of change just keeps accelerating.
It's true.
Yeah, there's one system I'm particularly curious about. The head-up display, or HUD. I've seen it in movies where the pilot can see all the information projected right on the windshield.
Oh, yes, the HUD. It's a classic. And it's not just for fighter jets anymore.
Right.
You see them more and more in commercial planes now. Even some smaller planes are getting them.
So how does it actually work? Is it really projecting onto the glass?
It is. A projector beams all that key data, airspeed, altitude, heading, navigation cues, even warnings, onto a transparent display, right in the pilot's line of sight.
That makes a lot of sense,
Uh-huh.
especially during takeoff and landing.
Exactly. When those split-second decisions are so crucial. But it's not just about safety. It also reduces pilot workload.
Okay.
They're not constantly having to look back and forth
Makes sense.
between the instruments and what's outside.
So it's all about streamlining the flow of information.
You got it. Making sure the pilot has what they need when they need it.
And that's a theme we've seen throughout this whole deep dive, hasn't it? From those early pressure gauges to these amazing HUDs. It's all about getting the pilot the information they need
Yeah.
in the most intuitive way possible.
You nailed it. And it's not just about the instruments themselves. It's how they all work together to create this seamless flow of information, from sensors to displays.
And ultimately to the pilot's brain, so they can make the best decisions and keep the plane flying safe. But with all these systems, with all this automation, it makes you wonder, are pilots becoming less important? Are we headed toward a future where planes fly themselves?
That's the big question, isn't it? And it's one we're going to discuss
Yeah, we'll definitely dive into that.
in the next part of our deep dive. That's a question a lot of people are asking. And
Yeah, it's a big one.
it is a big one. And, the technology is definitely moving in that direction. I mean, we've already got autopilots
Right.
that can handle so much, even landings in some cases. And, some companies are working towards fully autonomous aircraft.
Yeah, I can see how that would make some people nervous. I mean, a plane flying itself with no pilot, that's a little unsettling.
I get it. It's big change. But it's important to remember that aviation has always been about pushing the limits.
Yeah.
Always innovating, but never compromising on safety.
Right.
So the goal with automation isn't to replace pilots entirely. It's to enhance their capabilities and make flying even safer and more efficient.
So it's about creating a partnership.
Yeah, exactly. Human and machine working together.
Each playing to their strengths.
Exactly. Think of it like this. Automation can handle the repetitive tasks, those precise calculations, the split-second reactions that might be difficult for a human. And that frees up the pilot to focus on the things that humans are really good at, the higher level decisions, the strategic thinking, the complex problem solving.
So it's not about taking the human out of the loop, it's about elevating the human's role.
Exactly. It's about making the pilot more effective, more efficient. But what does that mean for the future of pilots then? What skills are going to be most important in this new world of automation?
Yeah, what do future pilots need to focus on?
Well, technical skills will always be essential. Pilots need to really understand those aircraft systems,
Right.
how they work and how they interact. They need to be comfortable with all that advanced technology, and they need to be able to interpret the data those systems are producing.
So it's not just about stick and rudder skills anymore.
Not entirely. It's about systems management, data analysis, all that high-tech stuff.
But it's not all about tech, is it?
You're right. It's not. Those soft skills, those human qualities, those are going to be even more valuable. Things like judgment, decision-making, communication, situational awareness.
Yeah, those things that are really hard to program into a computer.
Exactly. And those are the things that are going to separate good pilots from great pilots in the future.
So you need to be able to think ahead, adapt to changing conditions, make good decisions, even when things get unpredictable.
That's the heart of it. It's not just about being a pilot. It's about being a leader, a problem solver, that steady presence in the cockpit, even when things get a little rough.
It's inspiring to think about how these technologies are pushing us to get better, to evolve, not just as pilots, but as humans.
I agree. It's an exciting time to be in aviation.
As we wrap up this deep dive on flight instruments, what's the one big thing you'd like listeners to take away from all this?
I think the key takeaway is this. Flight instruments, in all their forms, are more than just gadgets, They're the result of incredible human ingenuity, the desire to make flying safer and more efficient. They're tools that allow us to push the boundaries of what's possible, to connect across huge distances, to experience the wonder of flight. They're pretty amazing.
Beautifully said. And if you're feeling inspired and want to learn more, I definitely recommend checking out the FAA Handbook.
Oh yeah, it's a great resource. And it's free online.
So that concludes our deep dive on flight instruments. I hope you all enjoyed the journey. If you have any questions or topics you want to explore in the future, just send us a message. Until next time, keep your wings level and your curiosity high.